Okay, so let's get going. Does anybody need a 4.4? 4.4 from last time? So we just started looking at this last time. So you should have one, unless you were not here last time. And this is just sort of kind of a review, I'd say, up to now. We've been talking about this idea of basis of a vector space or a subspace. And there are two aspects to what it means to be a basis, right? It's got to be a set of linearly independent vectors, and the span of the set of vectors has to be the space or the subspace that we're talking about. So the set of all linear combinations of the basis vectors is the actual space or subspace that we're talking about. And another thing you guys got to know, so we can, right? If we take M by N matrix, you guys now or soon should know how to find a basis for what's called the null space of A, find a basis for the column space of A. So my handouts kind of go on and on about the theory, but for testing purposes, the thing I'm going to ask you to do is, here's a matrix, find a basis for the null space, find a basis for the column space. So if that's not clear, you got to let me know, all right? We're going to move on from that today. And we're going to continue on with this 4.4 handout. We're going to talk a little bit about what it means to have different bases in the same vector space, okay? And there's that exercise down at the bottom, which I'll paraphrase here on the board. I want you to show that this set of vectors, 1, 1, 0, 0, 1, 1, and 1, 0, 1 is a basis for R3. And I said there we must show that. Actually, we're not going to show those two facts at the bottom, but what this means, maybe it's worth writing, that the span of those three, so the set of all linear combinations of those three vectors, is equal to R3. And those three vectors are linearly independent. And so one approach you could take to this, say if this was like a brand new concept or a concept all by itself, you could actually try to verify these things, that the span of those three is R3. That's a problem we know how to do as a separate exercise. And then you could also verify that those three vectors are linearly independent. That's a process we know how to do. But if you turn a page, I kind of give it away by writing this. It's really the invertible matrix theorem. So that long list of all those equalities mean these three vectors form a basis of R3 if the matrix we get having those columns, those vectors as columns, so 1, 1, 0, 0, 1, 1, 1, 0, 1, is invertible. Because if this matrix is invertible, what's implied is that its columns are linearly independent, and the equation AX equals B is has a solution for every B in R3. That's what it means for these three vectors to span R3. So when you see those directions show that those three vectors form a basis for R3, we now have enough theory that we can show that just by showing that this matrix is invertible. Okay. So how do we do that? We actually have several different ways of showing that 3 by 3 matrix is invertible. We could go through our process where we write 1, 1, 0, 0, 1, 1, 1, 0, 1, and then right next to it the identity matrix. Right? We could go through that process of finding to find A inverse. And I'm actually going to use that for something. How else could we show A is invertible? What else could we do? Could show the determinant is non-zero, or show determinant of A is not 0. So that's an alternative. Okay. It looks like it's not too hard to calculate the determinant of that. So that would be fine. Now, I'm actually going to take this route because I want to look at that inverse matrix. And what we get, there is an inverse. And I did this ahead of time once again. Where'd we go? I get a half, negative a half, negative a half, a half, a half, a half, negative a half, a half. So there's a lot of halves in there. What I can do is, just because I want to work with this a little bit, so A inverse exists here. And because I have a 1/2 appearing in every entry like that, I could factor out a 1/2 from the matrix expression and write that as 1/2 times 1, 1, negative 1, negative 1, 1, 1, 1, negative 1, 1, and call that A inverse. So since A inverse exists, the three vectors form a basis for R3. Okay. We already talked about how any invertible 3 by 3 matrix is going to have columns that can be thought of as a basis of R3. There are infinitely many of those bases, all right? So that takes us to the next exercise. So I'm not saying you can't, there's nothing wrong with just computing the determinant there and showing the determinant is not 0. That would also answer that question. I just wanted to have the A inverse handy here. Okay. So the next exercise is take this particular vector, 1, negative 2, 4, in R3, and find the coordinates of x relative to the basis 1, 1, 0, 0, 1, 1, and 1, 0, 1. So I'm using set brackets here to refer to this collection of three vectors. I'm not writing span. If I wrote span in front of it, that would mean the span of those is all of R3. Here I'm just talking about those three. So sometimes we have fancy ways to do things, and sometimes we just have these sort of nuts and bolts ways to figure things out here. All this question is asking us, and I wrote it on the handout for us, okay? So I shouldn't have had to write this last line, but what we're going to do is find scalars C1, C2, C3, such that C1 times 1, 1, 0 plus C2 times 0, 1, 1 plus C3 times the third one, 1, 0, 1, is that vector 1, negative 2, 4. Okay? C1, C2, C3, we call the coordinates of this guy that we started out with relative to this new basis, right? They're the scalar weights that would produce the linear combination that gives us 1, negative 2, 4. On the first page of the handout, that theorem at the top, that just says, all that's saying is there is only one way this can be done. So there has to be a unique solution to this for C1, C2, C3. Now, again, this is just an algebra problem again, but we can write this as we could take the matrix I've been calling A times a column vector C1, C2, C3 to get 1, negative 2, 4, right? So we're solving a matrix equation. This is our A. One way, again, I tend to point us in a certain direction, but I just, often there are many, many paths you can take, and I don't want you to think that you just have to take that path. One way is to use the augmented matrix. That's sort of our non-fancy way. Let's do that. Another way to solve is to use A inverse, since we have it, right? So A times C1, C2, C3 is equal to, I'm going to leave a little space here on the left, 1, negative 2, 4. I can multiply by A inverse on the left. These guys cancel out. So C1, C2, C3 are just, as the column vector you get when you take A inverse times that 1, negative 2, 4. And I just erased my A inverse, but somewhere here I have it. Remember I had it with that 1/2 factored out, 1/2 times, coming down the columns, it was 1, negative 1, 1, 1, 1, negative 1, negative 1, 1, 1, times 1, negative 2, 4. So I'm just making use of that A inverse here and carry out that matrix multiplication. I have it written on this piece of paper. What I get is negative 5/2, 1/2, 7/2 for the C1, C2, C3 values. Okay. So negative 5/2, 1/2, 7/2 are the, I'm going to say B coordinates of x equals, what was our original x was 1, negative 2, 4, where B, curly B, is that basis we were working from, the columns of A, right? 1, 1, 0, 0, 1, 1, and 1, 0, 1. So sometimes we're going to give a basis a name. So B is one basis. In our lovely notation here that we got to get used to, the book likes to write x in brackets with a little b down to the right. Sometimes I feel like the more intimidating notation gets, the simpler the idea is that it represents. Because this is just negative 5/2, 1/2, 7/2, that column vector. Okay? That's our notation for B coordinates. If we go back to this equation, this matrix A the B coordinates of x give us that vector x. I just want to kind of go back and plug in that funny looking B coordinate notation for us. And I did give you room on the next page, which unfortunately, if you're like me, I never notice till I am done with the problem and turn the page and see there's more room. Sorry about that. And now we got to look at this next exercise. So now we're in a different situation, all right? Find x if our basis B is 1, 0, 1, 1, which is a basis, I should have written these words in, for R2, we're just looking at an R2 situation. And if the B coordinates of x are 3, 5. This is just the reverse direction of what we just did. So instead of starting out with an x and finding its basis coordinates in another basis, we're saying we know the coordinates of x in this basis. Here's the basis. Who is x really, right? What are the standard coordinates of x. So when we write x by itself, this always means standard coordinates. We just got to figure out how to interpret this notation, right? We can just write it down. No inverse to calculate. We just have to know how to interpret this. Do you see what x is going to be? X is going to be just a linear combination of these two using these weights, right? I mean, you could write it as 1. Well, actually, I want to go backwards through it. Let's go backwards through. Let's just say it's 3 times 1, 0, because that's saying it's the first coordinate in this basis, plus 5 times 1, 1. So that's the second coordinate using that basis. And so we can just plug in here and get 3 plus 5, 8, right? 3 times 0 plus 5 is 5. That's that, boom, okay. But I think we also kind of want to make an observation here that we can describe x, so the standard coordinates, as I could take this matrix that has the basis vectors as columns, right, times the b coordinates of x. And we're going to call this guy, it was A in the previous example. We're going to start giving it a name now. Let's load down our notation. This we're going to call P sub B, okay? I don't know why they use P suddenly. I'm just going along with our book's notation. So it's a particular matrix. In this, it's a square matrix here. And the columns are just the B basis vectors. So the B refers to the basis that's given by the columns of that matrix. So turn the page. And what's at the top of page 4 really just sums up what we just said now. And this, I hope this notation is not so intimidating now. Let B be a basis for Rn. So we're talking in generality here. So B1 through Bn, we have n vectors there. Define this PB as, that's just saying matrix with the basis vectors as columns. Then for any vector x in Rn, PB is equal to, or PB, this guy, times the B coordinates of x are going to be the standard coordinates. And I had a note here to myself. Yeah, this is something that you don't have to write down, but I like to call the standard basis of Rn E. So for R2, this E is just the 1, 0, 0, 1. And what's PE? Just playing tricks with your minds here, I feel like. Just matrix with those columns, PE is always going to be the identity matrix. So here it's I2, but this would work just as well in n dimensions. It would be IN. And the standard coordinates for a vector which we denote just x alone. We kind of think of that as the vector x. You can say that's equal. Is the same as saying, using this boxy, brackety notation, xe. Like, that helps me thinking of that standard basis as just another basis, like all these others that we've talked about. But if you don't really need that right now if that's just driving you crazy. Okay. All right, now let's do that next exercise. Where we're working with one of these polynomial spaces again. And please, like, speak up, because I always feel like with these polynomial spaces, I tend to, like, just jump to conclusions. And you guys are sitting there going, what? What does this have to do with linear algebra? So please let me know if this is confusing. So we're talking about P2 is polynomials of degree less than or equal to 2. That's a vector space. And the standard basis, what we will call the standard basis of P2 is the constant polynomial 1, the polynomial t, and the polynomial t squared. So for that vector space, this is what I would call the curly E. Okay. Now, let B be the set of 3 polynomials, 1 plus t, 1 plus t squared, 1 plus t squared. And the first thing we're going to show is that B is also a basis for P2. Okay. So we're in this more abstract setting. We don't have a matrix here. Like, we've been doing all these things with matrices and columns. I realized in my notes I had this real fancy answer, and I thought maybe we shouldn't be fancy with this. Maybe it's better, since we've just gotten used to this idea of basis, let's just do it the long way, maybe. It's long, but maybe just the easiest to understand way. What do we have to show if we want to show that's the basis? Yeah, independence, and that the span is P2, right? So show maybe independence and that the span is all of P2. So those are two separate things to show. How would we show independence? Well, we don't have columns to put in a matrix and see if the matrix is invertible, right? We just have these polynomials. So what do we have to do? Yeah. Suppose we have, yeah, exactly. So Helena, say it again.
So we need to show that the sum of those vectors will be 0 when all the coefficients.
Yeah, so if we take a linear combination of these three polynomials, thinking of them as vectors, but just take a linear combination of these three, and we get 0, we have to show that implies that each of the coefficients must be 0. All right? Now, we got to introduce some notation to do that. You could use ABC, X, Y, Z. I mean, there are a lot of letters you could use, C1, C2, C3. I might use C1, C2, C3 just because we've been using that C notation, but there's no magic to this letter C here. So I'm saying suppose C1 times 1 plus T plus C2 times 1 plus T squared plus C3 times 1 plus T squared equals 0. We need to show that this implies that C1 equals 0, C2 equals 0, C3 equals 0, right? That's the only solution. That's what linear independence of those three would mean as polynomials. And we can just do this as an algebra problem. We got C1 plus C1t plus C2 plus C2t squared plus C3 plus C3t plus C3t squared equals 0. I'm going to combine like terms here. I have a constant C1, C2, C3. I'm going to group those together. Those are the constant terms, right? And then my t coefficients are C1 plus C3t. And my t squared coefficients then, hopefully I didn't miss anything, are C2 plus C3. Now, this isn't just 0, this is the 0 polynomial. And by that I mean it's like 0 plus 0t plus 0t squared. That's the only polynomial that's equal to 0 for all t. And so the coefficients must each be 0. C1 plus C2 plus C3 must equal 0. C1 plus C3 equals 0. C2 plus C3 must equal 0. Okay. So the coefficients must each be 0. And so we can solve for C1, C2, C3. And that's even a linear algebra problem, okay? Like you could even set up a matrix equation and solve. But it turns out C1 equals 0, C2 equals 0, C3 equals 0 is the only solution. You can verify that. So I don't think I need to fill that step in for you. And thus our set is linearly independent. Now, it almost seems like a matrix is popping back into the situation, and there is a way to just turn this into a matrix problem right off the bat, but I didn't want to push that yet because I just want us to think it through that this good old-fashioned checking for linear independence We just crank it out, and we find out the only way that can happen is if C1, C2, C3 are 0. Now we got to check the second condition. How are we doing on time here? Check the span. And that's like saying if we take any element of P2, can be expressed as a linear combination of our of the B vectors, or the B elements. So how would we say that? Now, again, notation. Pick any polynomial in P2. I might describe it as P of t equals A plus BT plus CT squared. Show that we can find C1, C2, C3 such that C1 times 1 plus t plus C2 times 1 plus t squared plus C3 times 1 plus t squared is equal to this P of t, A plus BT plus CT squared. I'm not too far in the corner, right? Now I am going to try to give us a slightly fancy answer for this. This is the same thing we wrote over there. So I can multiply out and rearrange the coefficients. And am I taking too many steps if I say we want to check C1 plus C2 plus C3. We want that equal to A. We want C1 plus C3 equal to B. And we want C2 plus C3 equal to C. So can we solve for C1, C2, C3? Did I take too big of a jump there? So I'm doing I just didn't write out the steps of what we did here, but instead of 0, 0, 0, which really are like the constant, the t coefficient, the t squared coefficient here, it's, the A is the constant, the B is the t coefficient, and the C is the t squared coefficient. I'm not going to go through all that. Watch what I'm going to do and what you can do too. I'm just going to rephrase this as a matrix system, right? I can think of that as a matrix times C1, C2, C3 equals A, B, C in that form. So what I'm taking this information, which just looks like a system of 3 equations and 3 variables, writing it in vector form. C1, C2, C3 are my unknowns now, right? A, B, C are constants, and then my coefficients are just 1, 1, 1, right? And 1, 0, 1, and 0, 1, 1. What am I going to pull out of my hat? I'm not going to try solving this, right? This, you should think, our notation looks a little bit different, but you should think AX equals B. A is square. Invertible matrix theorem. If this matrix is invertible, then there is a solution for every A, B, and C in R3 now. We're actually working with, we turned it into a regular Rn kind of vector problem. Okay. And how do I verify invertibility? I can try to find an inverse. I can check the determinant, which is what I'm going to do, and maybe expand along the third row. And let's see, plus, minus, plus. I get plus 0 times something, minus 1 times a 2 by 2. I think it's 1, 1, 1, 1, right? Uh-oh, I hope I... And then I'm going to have plus 1 times 1, 1, 1, 0. I hope that wrote that down. This is 0. 1 minus 1 is 0. Second term is 0. So that's why I was going, uh-oh, I better get something that's not 0 here. And I think I get 1 minus, I think I get negative 1. So it's not 0. So by the chain of logic here, we know this set of equations has a solution for any choice of A, B, and C. And so therefore, the span of our basis vectors of our B vectors must be all of P2. Boom. I think that's just part A of that problem. Right? So what you should be thinking here is like somehow, even though we're talking about these polynomials, this is just turning into a R3 kind of matrix problem. And there is a way with our, as we expand our knowledge, that we can jump right to the R3 matrix problem. There's certain equivalence here. But I didn't want to do that because I just thought this level of detail gets back to what a basis really is. And we're just working from polynomials. But because we end up with systems of equations, we end up with, so I just think it's kind of using stuff we know, right? If we didn't have invertible matrix theorem, we'd kind of have to go through one of those calculations with the augmented matrix. Remember where the B got all complicated and you had like A1 plus A2 minus A3? Like, so we don't have to do that anymore. We don't have to find what the solutions are. We know that no matter what I put here for A, B, and C, there will be a solution from our theory. Okay, so a couple more minutes. We gotta. So I know I feel like I slowed down. We might not get all the way to the end of this, but we're actually there's just a little bit more theory. After the part B, we gotta do our Per B. Questions? Is that? I hope you're like, yeah. I hope you're not, It should, like it's just weird. You can approach these things in a very like abstract, theoretical way. This was sort of like get your hands dirty kind of way where we just cranked it out is what we say in math.